Hi guys. So let's start off with one of the examples that I was talking about at the end of class, but I didn't really get to finish fully going into it. So this is just to wrap up what we did at the end of last lecture. And there's a reason that I wanted to do this example because, well, it'll be useful if you guys get the hang of using the standard normal, doing calculations with the standard normal distribution. Because remember how to take any normal and make it standard normal. So let's do this problem to see an example of that. All right, so we're talking about Bitcoin. Anyone own Bitcoin in here? Oh, really? Nice, man. I wondered if maybe we had a few Bitcoin millionaires. So we're going to assume that the price goes up with a probability of 0.6 on any given day. So that's the success probability. P is 0.6. And we're looking at the actions over 200 days. So those are 200 different Bernoulli trials. In other words, 200 is like our n. If I let x be the number of days over the next 200, that, you know this symbol? Yeah, it's the Bitcoin symbol. I had to look that up. All right, so the number of days over the next 200 that Bitcoin goes up. Then since n is 200 and p is 0.6, so NP is 120. We would expect it to go up 120 days. And n times 1 minus p is 80. Why am I checking what NP and n times 1 minus p are? Yes, right, yeah. I want both of these to be bigger than 10, right? So the point is this number is bigger than 10, and this number is bigger than 10. So we can approximate the binomial of 200.6 distribution with a normal distribution with mean being the expected number of successes or days that the price is going to go up. And the standard deviation is, well, we had a formula for the standard deviation of the binomial distribution. NP 1 minus p. So 200 times 0.6 times 0.4, which is about 6.93. Yes. Cool. So if I want to do calculations, it'll be easier to convert to a standard normal. So this is the part of the problem that I wanted to sort of impress upon you is where we let z be the standardized version of this random variable. So we subtract the mean and divide by the standard deviation. When I say approximately n01, I mean i.e. approximately has a standard normal distribution. Cool, okay. Then what did we want? We wanted to find out the probability that it went up on more than 100 days. So we wanted the probability that x was greater than or equal to 100. Here's the part where it seems like a lot of people get lost is I standardize both sides of this event. So let's subtract 120 and divide by 6.93 on both sides. But then this right here is exactly z. So this is the same as the probability that z is greater than negative 20 over 6.93, which is the probability that z is is approximately the probability that z is greater than negative 2.89, which we can get from a table as right there. I plugged in 2.89. Oh, nice. Finally got my pen to connect with Bluetooth to my laptop. Cool, okay. So as you can see, we're interested in this red region right there, the bigger red region. This one, well, now it's gold. So we get approximately 998. So yeah, pretty sure Bitcoin's going to go up on at least 100 days. Cool. Any questions on this before we get to today's lecture? Okay. Yes? Yes, there's a lot of z-score calculators actually which allow you to work with unstandardized normal distributions. Like, yeah, so plenty of websites or calculators will do that for you as well. It's good to know how to do it with the standard because you may not always have a computer or a calculator at hand, in which case you might have to rely on a table. And they're not going to give you tables. If they're going to give you a table, it's only going to be for the standard normal. So you should know how to do that. Plus, we'll make reference to that type of calculation multiple times in this course, including in today's lecture. So today we are going to talk about confidence intervals. And let me sort of present a problem for you to think about. which will be a prototypical problem that we are going to work on answering today. So here's a problem for you to think about for today's lecture. About the drinking age. So I got some data from a survey of 87 UCSD students, and it turned out that 64% of them thought that the drinking age should be lowered. Okay. It so happens that those 87 students were from this class, but I'm going to make the assumption that this class forms a representative sample of all UCSD students. I'll discuss later how valid of an assumption that may be, but let's assume that 87 randomly selected UCSD students, of 87 of them, 64% said the drinking age should be lowered. What does this say about the beliefs of the entire UCSD student population? Is it really 64%? Well, if this is all we have to go on, then certainly our best guess is that 64% of UCSD students feel that the drinking age should be lowered. But how sure am I about that? I'm going to try to find a confidence interval, or in other words, a margin of error where I can say that I'm 95% confident that the actual number of UCSD students that feel this way is in this interval. That is what the question of confidence intervals is about. So here's what our goal will be today is confidence interval, which I'll often just abbreviate as CI. So in our example, the sample proportion was 64%, and the population proportion is what we're trying to determine. So we're going to estimate P. With p hat, if np is greater than 10, and n times 1 minus p is greater than or equal to 10, those are the conditions under which the approximately normal condition applies. And the sample mean is, well, the same as the population mean. And the sample standard deviation is, I derived this formula, I think it was last lecture. It's p times 1 minus p over n. right? So that's sort of a measure of the error that we should expect in these sample measurements. You can refer to, was it last lecture when I did this? I think it was, okay, yeah. Refer to last lecture to refresh yourself on this formula for sample proportion. It's like the binomial standard deviation divided by n is where this comes from. But actually, we can't even use this because we don't know what p is, right? We're trying to figure out what the population proportion is. So we have, before we can do that, we have to estimate what our standard deviation is. And that's what, thus we introduce the concept of standard error. So since p is unknown, we're going to estimate the standard deviation of p hat by the so-called standard error. Standard error. And you, instead of SD, you use SE to abbreviate it. And what's the standard error? Well, since we don't know what P is, let's just replace it with our best guess for what the sample, with what the population proportion is. And our best guess is the sample proportion. So all I'll do is just put hats on the P's. And that's our standard error, P hat, 1 minus P hat over n. So that is something that we're going to have to repeatedly make use of today. So that's an estimate. It's always an estimate of the standard deviation. Cool. So now that we have this sample mean and it's approximately normal, we can standardize it, like I was doing in the example before class. So p hat minus p over the standard error. I know there's like multiple approximations being made here, but this is then approximately a standard normal. Okay. Now comes one of the tougher concepts that I think is going to be explained in this course. I've never had to explain it to someone, but I'm going to try to now, which is a confidence interval. So, all right. Remember the 68, 95, 99.7 rule? Here, let me just point this out in an example. From the 68, 95, 99.7 rule, what did that say? That said that within, let's say, 2 standard deviations, there was 95% of the data. The 95 here refers to 95% of the data lives within 2 standard deviations of the mean. And actually, this is a lie. Because it's not exactly 2. If you plug it in on a z-score calculator to find what z-score corresponds to 95, It's very close to 2. We've been saying 2, but it's actually, we're going to be a bit more precise now and replace it with 1.96. So a z-score of 1.96 corresponds to the probability that a standard normal between those two z-values is 95%. So I'll write 1.96 instead of 2. Okay, so 95% of the data lives within 1.96 standard deviations. So my population parameter there is a 95% probability that my population mean is within 1.96 of my population mean. Did I say that right? Let me write that down. There's a 95% probability that p hat minus p is less than 2 standard deviations away from each other. Or, sorry, not 2, 1.96. That's exactly what it means to say that 95% of the data lies within 1.96 standard deviations. Or I could write it a little bit differently, that that p hat minus 1.96 times the standard deviation of p hat is less than p hat plus 1.96 times the standard deviation of p hat. Or approximating the standard deviation of p hat by the standard error of p hat there is 95% probability that p hat minus the standard error of p hat, p hat minus 1.96 times the standard error of p hat is less than p hat plus 1.96 times the standard error of p hat. So what's the error, though? Like, if there's 95% probability that p and p hat are within this so-called margin of error, there's still a 5% chance that it's not, okay? So that could happen. That 5% chance is the probability that the population proportion is not within this interval, okay? I'm now going to rewrite everything I just wrote down, but a bit more generally. So I'm going to make this argument. I'm basically going to make the same argument for you twice in a row. So more generally now, let alpha be the probability that we are willing to tolerate being wrong. All right, so alpha was 0.05 above in what I was just saying, which usually is what it is, by the way. So this leaves a 1 minus alpha probability, or confidence, if you will, that we correctly trap P in the confidence interval. So here's a picture. Let's say this is a standard normal. And that this is 0. I want to trap 1 minus alpha of the probability in a certain range. So in here, I need 1 minus alpha of the data. But that still leaves a little bit on either end. So there will be alpha over 2 left over there, and alpha over 2 left on that side. But what are the two numbers, the two scores that go right here? I'm going to call them z star, and by symmetry, this one is negative z star. So we choose z star such that this is the case, such that the probability of a standard normal random variable being between negative z star and positive z star is 1 minus alpha. What was z star in the previous example? 1.96 in the example above. Good, okay. Yeah, which is close to 2, but yeah, we'll say 1.96 now. And this is for okay, so having chosen z star, since p hat minus p over the standard error of p hat is approximately a standard normal, we have, okay, so you guys like this part. We have that 1 minus a is approximately the probability that negative z star is that this standard normal unit vector is between negative z star. I said unit vector. That's my other class. That this standard normal random variable is between negative z star and z star. Which I could also write as the probability that negative z star times the standard error of p hat is less than p hat minus p is less than z star times the standard error of p hat. Or I want to subtract p hat from everything, so I'm just going to multiply everything by a negative, if you don't mind. Make this a positive, make this a greater than, make this a positive, make this a greater than, and make this a negative. So I have the probability that negative z star is less than p minus p hat is less than z star times standard error of p hat, which by I can just add p hat to everything, is the probability that p hat minus z star times the standard error of p hat is less than or equal to p is less than p hat plus z star times the standard error of p hat. And that's my confidence interval. So let me pause for questions. I know this is a lot I'm throwing at you right now. Any questions, or did I make any mistakes or typos here? Let me just... Here? Yeah, I just wrote it in the reverse order. Yeah. Yes?
So I was checking the Z table, but then it would the probability for 95 was 1.6.
Oh, probably checking the wrong statistic. Let's check, man. So if I... Let's see. I want this one to be 95. You dig it? Yeah. So if I calculate that one to be 95, I get z equals 1.96. Any other questions? Yeah, Rachel?
This is a little dumb, but when you're working in a lab and you conduct a p-value test, and your number is greater than 0.05, what does that mean?
Let me not get into that right now. We're going to get to that later. Okay, so let me write out what the confidence interval is. Okay, so assume this is all right. Let's continue on. Therefore, what's the big result of all this? The moral of all this math that I just did is we have a confidence interval, and it is p hat minus z star times the standard error of p hat and p hat plus z star times the standard error of p hat is our 100 times 1 minus alpha % confidence interval. It was 95% when alpha was 0.05, like in the previous example. And we have a new terminology. The margin of error is ME equals Z star times the standard error. What are you guys all talking about? So, okay, if that's the margin of error, right, so you can say that the confidence interval is p hat minus the margin of error up to p hat plus the margin of error. Okay, so let's solve that problem that I gave you at the beginning of class. Solution to, okay, what the heck was that problem? This one. All right. So in this case, we had 87 was the number of people in the sample. And 64 was the sample proportion, p hat. P hat is a random variable. We ran an experiment, and it turned out that it was, and the result of the experiment was 64%. But if you ran the experiment again with a different sample, you would get a different p hat. So using those numbers, let's see. We also want to, since we're doing a 95% confidence interval, so that means alpha is equal to 0.05. And as just discussed, Z star is 1.96. So the margin of error for our estimate is, what was it? It was Z star times the standard error. So it was 1.96. The standard error was our best estimate of the standard deviation. So in this case, we get p hat was 0.64. 1 minus p hat is 0.36. N was 87. This whole thing comes out to 0.10. So we had a 10% margin of error in our estimate of the true percentage of UCSD students that feel that the drinking age should be lowered. So what's the 95% confidence interval? Apparently 0.64 minus 0.10 up to 0.64 plus 0.10, or 0.54 up to 0.74 is our 95% confidence interval. So we can be 95% confident that between 54% and 74% of UCSD undergrads favor lowering the drinking age. Yes?
assume like, oh, you can assume that there's more than 870 students at the school, or is that something else I'm thinking of? Because isn't there a 10% rule when you're sampling and like you're not returning or something like that?
Oh, yeah, right. Yeah, so UCSD has, what, like 30,000 students or something? Yeah, so, yeah, sure. Sure, good point.
So is that like the same thing as checking the NP and N?
The book calls that the success failure condition. So yeah, it's two separate conditions.
Okay, but we wouldn't do line or we wouldn't check the 10%
Actually, yeah, technically, yeah, we should. I didn't bother to do it here, but it does. Is the 10% condition satisfied here? I can do a quick check. Let's see. Yeah, 87 times 0.64. That's bigger than 10, and 80. Okay, yes, right. I didn't even mention that, but yes, you were right. I just assumed that the population of UCSD students was way more than 10 times 87. Yeah. Okay, so what's the interpretation of this? Yes. That you said it pretty good. It's kind of got to watch your words when you speak about confidence intervals, but I would say it pretty close to that. So yes, we are 95% confident that our interval contains p. What does that mean? In that if we repeated this sampling procedure many times over, and we took a whole bunch of different samples of size 87, then what? %95 of those samples, 95% of the confidence intervals that we generate from this process would contain the true population proportion. What's the random variable here? It's kind of weird with confidence intervals. It's the interval is the thing that's random. The population parameter is the thing that's fixed. So try to keep that straight. Like, what's the thing that we are saying? We are making probability statements about. We're making probability statements about the interval. The population parameter, it's some fixed number. It's either in the interval or it's not. It doesn't, as I've discussed, it doesn't make sense to make probability statements about some fixed number. So here's a couple warnings. First, don't say that P has a 95% probability of being between 54 and 0.74. because p is not a random variable. That said, even though I just said not to do this, a lot of people say this anyway. So you might hear people say this because they get kind of loose with the language, but technically you shouldn't be making probability statements about p. You should be making them about the interval. And then here's another thing about confidence intervals. So they're only valid when the samples are valid, when they are representative and random. So I got the data for UCSD student thoughts about drinking ages from you guys, from Math 11 students that are taking my class and come to lecture and respond on Socrative, all these different biases that might make this not a representative group of all UCSD students. Like you could imagine if I had gone to a campus meeting of Alcoholics Anonymous, I might get a different sentiment. Or if I had gone to a campus meeting of the Campus Mormon group, right? Like maybe they might have felt differently about the drinking age as well. So it's a valid question, and maybe this wasn't a valid representative sample, but I assumed it was for the purpose of my example. Finally, one final warning. Remember the 95% confidence interval? That still leaves a 5% chance that we're wrong. So they don't always contain it. Now, I'm not going to have time to finish this problem, but I'll have to do this one next time, which is problem 2 here. Let me just show you. So remember when I was talking about presidential polls, and I said that some of the Gallup polls were able to accurately predict the results of presidential elections to within like a couple of percentage points. How big were the polls? I mentioned one that was 3,000, which is about how big they do them now. So the trippy thing is that 3,000 number, I'm going to show you where it comes from. And it doesn't depend on how large the overall population is, right? It could be valid for a population of 1 million or 1 billion or even 1 trillion, as long as you specify a specific margin of error that you're looking for. It just comes out of the math that the number you needed in your sample is just some fixed number. And it's around 3,000, as I'll show you next time. It involves inverting the formula for margin of error and solving for n. So a little bit of algebra involved. So we'll practice that next time. All right, thank you. Sorry?
What does the third warning say?
They might not contain the true proportion. May not Let me rewrite that.
You're 95% confident that within samples of 87, that the interval between 0.54 and 0.74 should contain P or something. I don't know. Because like how back when I took AP Stats, I would always say like the wrong way you said.
Yeah, a lot of people say it that way. So, like, people probably will say it this way, but really, more specifically, what there is a 95% probability is